All right, 5.5c, and quite possibly one of my favorite sections of all of the sections of 5.5. And welcome to what I refer to as the multi-angle. Yeah, it sounds kind of like you're in some kind of a thriller. Multi-angle. Yeah, it sounds crazy. So the kind of things we're going to be basically seeing today is some more trig functions or more trig equations that we're going to be talking about. But we're going to be stuck into situations where we have to solve equations that have multiple angles. For instance, we might be looking at situations where we're dealing with a 2x or a 3x or even, heaven forbid, a half x, all right, and etc. So up till now, when we were solving any of our trig equations, we've really not paid much attention to the fact that, like, say, sine of x equals 1/2. You've been basically dealing with an angle that has just been a singular one angle. Now, what happens if we end up doing something like 2 or 3 or a half on those? Well, it ultimately boils down to that we're going to solve them basically the same way, but there's going to be an extra step that's involved, and we'll have to divide out the coefficient for the actual x as we go along. Now, I'll explain all this. This whole entire concept of dividing it out in this extra step is going to be an idea of variable substitution. Okay, and we use a lot of variable substitution, specifically in pre-calculus, or even further along when we get to calculus, use a lot of variable substitution ideas, and I'll explain what you're going to do in those cases. Now, to be able to understand what these multi-angles do over a singular quadrant is you got to be able to really answer how many answers are you expecting there to be. Now, normally we would not have to think about that concept. We would just answer the answers that were within the first circle of the unit circle, and we would be done with it in that particular regard. Now, here's exactly what I mean. If I take, for instance, I'm just dealing with, instead of a double angle or even a triple angle or a quadruple angle, let's just think about what we would do in the single angle sense. Now, normally when we talk about something like, say, when is sine of x equal to 1/2, well, what we're really thinking about is we're thinking about the graph of sine of x, and we're really thinking about how it's being graphed. Let's take a small second to graph the sine of x, and we would realize that the sine of x would start here at 0, 0, and it would go up, and it would come back down, and it would come back up. And this is what it would do in a complete cycle between 0 and 2 pi. And we get an answer for pi right here somewhere in the middle. Now, the reason why we end up getting the answers that we do is because each one of these regions where sine is 1/2 are represented in the unit circle. And like in this section right here, when we draw this part of the unit circle up to this point, this is really representing quadrant number 1 when we draw that part on the actual graph. And then as soon as we continue further on it, this section right here is representing, oops, sorry, that's horrible, is representing, sorry, I can't draw real well, representing section 2 or quadrant 2. And we're really trying to find a level between 0 and 1 where the graph, it is hitting the graph at what specific angles it's going to generate the answer of 1/2. And that's why it gives you these answers right here, or sine is 1, 2, 3. That happens at pi over 6 and 5 pi over 6. That's would be the two answers that we generate. Now, the reason that you're seeing that now kind of visually, that it's the sine wave, and when is the sine wave equal to the y value of 1/2, that makes sense why it ends up giving you those two individual answers of pi over 6 and 5 pi over 6 is where it's going to actually happen. Now, let's talk for a second about what a doubling of the angle really means. Now, if I'm changing this whole concept to say that sine of x is now 2x, and when is it going to be equal to 1/2, now I have to really remember what this 2 does inside the actual wave itself. It basically means that in the normal interval between 0 and 2 pi, we won't see just one wave take place. We're actually going to see two waves because it adjusts the period. Now, see how we're starting to bring back stuff that we've seen in the past. So if I draw that same sine wave, but this time around, as soon as I get to here, only pi has taken place. And it's going to do another full wave before it gets back here down to 2 pi. It's 2 waves within the answer of 2 of that sine 2x. Now, if I draw in that 1/2 again, right here, and I just go, oh, oh, it hit it. Oh, it hit it again. Oh my gosh, it hit it 2 more times. So the answer here that we're basically expecting is that it's not going to have just the normal 2 answers. It's going to have multiple answers. And it's going to generate 4 answers that you have to actually come up with. Now, that is the general idea here. That when we see a doubling of the actual angle, we're going to see the doubling amount of the answers. So if I was saying something that was a triple angle, I would expect it to have 6 answers. Because there are technically 3 waves that are going to occur between there and 2 pi. Okay? 4x is going to generate 8 answers. Now, if I then generated a half x, or an x over 2, that would mean that the wave is going to get, it's going to show up less, not more waves, but less wave between the 0 and 2 pi. You're only going to see half of the wave, and ultimately that can lead to an answer of usually half the answers. Now, I'm not going to say that that one is direct result, because ultimately you can get still the same 2 answers between 0 and pi because it's in the first quadrant. So it's not nearly as likely that I can draw that connection. So we'll see some half angle situations too, but you're definitely going to get, I'm going to say, less answers for most of the time. Sometimes you might actually make the wave so lengthy that the actual answer doesn't actually, the range value doesn't hit the wave at that particular time at all. And ultimately, it can even be a no solution in some cases. So we'll see each one of those kind of scenarios, okay? Now, you're going to see these little circles that are throughout the actual notes, and this is an old style technique that Mrs. Worrell used to use, and she tried to explain it to me one time, and I don't understand it, okay? I do all of this basic idea stuff still just by thinking about what happens in the sine double angle. Now, the way I do it is not to map it out on these circles. What I do is what's referred to as variable substitution. So we're going to push this through what's called a variable substitution method. And what I'm going to do is, I don't like, and probably you don't like, the double angle that's sitting in this spot. So what variable substitution allows you to do, and you can do this in math when you run across very difficult ideas, is you can substitute something in for it. So you're basically saying, instead of me thinking of this as a 2x, I'm just going to write in its place the symbol for delta, which is a triangle. I like to use delta just because I think of all these questions as delta problems. And I'll be like, hey, delta is equal to 2x. And I'm just going to substitute a brand new variable in for that to make the problem easier for me to work on. So if I write this guy out as sine of delta is equal to a half, now the question has gone backwards in time to a kind of question that we're used to dealing with. You're like, gee, I totally get this question. It's really not that hard. The 2 answers that it could possibly be would mean that sine is 1, 2, 3. I'll put that up here on the side. Sine is 1, 2, 3 because we're thinking unit circle. It's got to be a pi over 6 answer based on ASTC. It's got to be in the first and the second quadrant in the first revolution. So we got to basically think about the first revolution. And we're going to get an answer of 5 pi over 6. 5 pi over 6 is one answer, and pi over 6 is the other. Now, these were equivalent to delta, all right? Now, I'm going to put delta over here on the far side. Oops, sorry, make it look like a triangle. Delta was equal to this value, and so is this delta was equal to that value. Now, this is where we use the substitution back into the solution. So we're going to put right here that this was 2x and this was 2x. We're going to substitute it back in, okay? Now, all we used the delta for was to solve a simpler problem. Then we have to set it equal to what it was originally, So that way it's got what's going on. Now, before I tackle what to do with this 2x part right here, I've got to remember that I need to be also able to write the all solutions to these, which is 2 pi k plus 2 pi k on each one of those, because it's going to be a solution for all the solutions that could be out there. Now, once you've resurfaced the delta and figured out what to put back in there, I'm just going to kind of erase it or think that it's not there, and now I have to solve for the actual x that it could be. And what that x is going to do here is you're going to have to actually divide everything over there by the 2 that's in front of this x to get the actual solutions of where it's going to cross. Now, those actual solutions are going to yield, and this one right here is going to be a half. You're going to multiply by a half or divide by 2. That would be 5 pi over 12 plus, instead of 2 pi k, you're going to say that it is pi k. And that guy will reoccur over and over again. Now, I'm going to show you what those answers will yield just in a second. This one is pi over 6, which ends up being divided by a half, and that's going to be pi over 12 plus pi k. And now we've got to really think, okay, these are the all solutions. These are the ones that will give you all the solutions that you need. But then we got to think about what these pi k's really do generate in terms of answers between 0 and 2 pi. So if I was thinking about between 0 and 2 pi, and I'm going to say 0 inclusive, and 2 pi, I would get answers at this one to be 5 pi over 12, but then I add a 12 pi over 12 to it, and another possible answer could be 17 pi over 12. That's going to be the 2 that are generated out of that one within one revolution. This one's going to generate the same kind of idea, pi over 12, but then I add another 12 pi over 12 here for pi, and I'll end up getting another answer of 13 pi over 12. And those are going to be your 4 individual solutions of what's going to be the answers here. Now, usually we put them in order, like pi over 12, 5 pi over 12, 13 pi over 12, then 17 pi over 12, and you got all the individual answers that you want. These 4 are the answers to the solution. And again, it has more answers because it was a double angle. It has more wave parts to hit, so it ends up generating more answers, okay? Now, that was probably your first try at it. Don't freak out. You're just going to see this variable substitution take over and over again. So I don't like to even like mess with it. I just think, oh, hey, that 2x is really a delta. And then I go, okay, what is cosine of negative 1/2? Well, cosine is 321. So that's going to happen at a pi over 3 location, and it's going to be negative, all students take calculus, at second and third quadrants. So the pi over 3's that are in the second and third are going to be 2 pi over 3 plus 2 pi k. And the other one is going to be in the third quadrant, which is 4 pi over 3 plus 2 pi k. Now remember that you were setting this whole entire stuff equal to delta. That was the answer what delta would be. But unfortunately, that's not what angle we're really dealing with here. We're really dealing with a 2x. And now I've got to run through this entire thing a division of 2, or if you really want to think of it, it's really like a multiplier of a half through the whole entire thing. So the solution you're going to get as an all solution is going to be 2 pi over 6 plus pi k, which will ultimately be 1 pi over 3 plus pi k. There's your all solution for that one. This one, if I multiply through by the half, I would end up with 4 pi over 6 plus pi k, and ultimately 2 pi over 3 plus pi k. Now, these are all solutions that you're basically going to give you every single answer, and it is very likely sometimes they might overlap one another. That totally happens, where like one overlaps the other. You just got to watch for it. We'll see maybe some of them that show up. So as I get my solutions, I just make sure that I don't run out of the 2 pi intervals. So I know that pi over 3 is 1. If I add pi to that, I would end up with 4 pi over 3. If I added this one would give me 2 pi over 3, and if I added pi to that one, I would get 5 pi over 3. And these would represent the 4 solutions to the answer of that original cosine double angle. All right? So the goal here is make an easier problem and then ultimately run that easier problem through the values and see what you end up coming out with, okay? So, triple angle, let's see what we end up getting. So you have to visualize that that's really not a triple angle, it's just a delta. So you solve the delta just like anything else. Well, when tangent is -1, it's going to be a pi over 4 reference. All students take calculus. It must be second quadrant and fourth quadrant. So it must be a 3 pi over 4 plus pi k. And I bet you we can probably get away with, 3 pi over 4 plus pi k. And the other answer, that's going to give them both. Because we really do have 3 pi over 4, and in the fourth quadrant we got the other one, which is 5 pi over 4. Now remember that this is equal to 3x. And I'm really going to multiply through this entire thing by a third, all the way through to generate the all answer, which is going to be 3 pi over 12 plus pi over 3k. Now, when you're trying to generate these answers, sometimes some simplification of this all answer really does help. 3 pi over 12 is really pi over 4. Okay, we got pi over 4 plus pi over 3k, and man, it's going to end up being that we're going to have to probably get this in 12ths so that you get the idea of what's going on. So you're going to have to add these two together multiple times to get it to come off. So an equivalence, I would basically say, would be saying, maybe I don't want to deal with this one in terms of pi over 4. Let's leave it as 3 pi over 12. And then write this pi over 3 one as pi over 12's 2. So we've got pi over, that would be 4 pi over 12. And that right there is an equivalent one to the one right next door. The reason why I'm doing that is because it helps me generate all the answers that I'm really searching for. The first one is going to be definitely this one, 3 pi over 12, which is really pi over 4. And then I'm going to add this one on there. I'm going to get another one, which is 7 pi over 12. And you just keep adding it on till you run out of the interval. So I get 7 pi over 12. The next one would be 11 pi over 12. The next one after that would be a 4 added on to the 11, or 15 pi over 12. That's probably not the best answer. That is actually divided by 3 in each case. 5 pi over 4. That's another answer for that one. And then I'll add on another 4, 19 pi over 12. And you're just like, gee, when is it going to end? Well, it's when I run out of the interval of 2 pi. Not there yet. Keep adding on 4s, because this would be 23 pi over 12. And at the moment I go over 24, which is 2 pi, now I've gone over the 2 pi interval. 2 pi's out here, and this represents all of the answers, and that makes sense that there should be 6 of them because this was a triple answer. So the goal here is simpler problem. Then once you get your simpler problem solved, put your multi-angle back in, fix it all the way through so you know what it's equivalent to in terms of x, and then you might have to do some adjustment with the all answer so that you can get common denominators and know what to add on. All right? Let's try it one more time. Example number 4. Multi-angle, I'm going to put a delta in that guy's spot. When is sine root 2 over 2? Well, that's going to happen at a couple of spots. It's going to be at pi over 4 plus 2 pi k, and it's going to happen in the second quadrant. All students take calculus, so that means we're going to get 3 pi over 4 to actually happen, plus 2 pi k as well, too. Now, this one's going to be equal to a 4x, okay? And what my suggestion would be to you guys is do the smaller one first, because ultimately you will end up probably generating an overlap on the second one in the first place. Sometimes they will overlap one another, where one lies on top of the other and just repeats answers. That can happen. If I divide by a fourth, or multiply by a fourth, excuse me, all the way through this thing, I would end up generating answers as such. It's going to give me pi over 16, ooh, that's sucky, plus 2 pi k over 16, over 4, like that, which is a pi over 2. Ultimately, though, I would probably find its equivalence in 16ths, so pi over 16 plus, now that guy in 16ths is going to be 8 pi over, I think that's going to be pi over 8 pi over 16. Yeah, 8 pi k over 16. Now that's going to be the answers that we're going to generate out of that one. Now let's see what the bottom one does. Bottom one, multiply through, I'm going to get 3 pi over 16 plus, again, probably that same exact thing, that 2 pi k divided by 4, which is equivalent to 3 pi over 16 plus 8 pi k over 16. Now, our expectation is there are going to be a lot of answers. There are going to be 8 of them, because that's a 4x. There's a lot. So let's see what we get out of this guy before we run out of the cycle. Pi over 16 is going to be one answer, and then I'm going to add 8 to that, or a 9 pi over 16. And be careful, some of these might reduce as you go along, and that one doesn't reduce. Add another 8 onto that, 17 pi over 16. Add another 8 onto that one, 25 pi over 16. And ultimately, if I keep adding 8, that one would go over, and we'd end up being too many. Well, now we got to go down the bottom guy. 3 pi over 16 is one of the answers. And then I add 8 onto that one, 11 pi over 16. And you're starting to see the pattern here. 19 pi over 16. And last but not least, I add 8 to that one. I would be at 27 pi over 16, and that would be the last answer. 8 total answers. Wow. Woo, that was fun. I like those. Now, if a multi-angle is going to give you lots of answers, then you would expect it's quite possible that when you go to a half angle, or even smaller fractions of half angles, you will definitely get less answers. Now, let's see how you solve these. They're solved exactly the same way. You ultimately are going to put a big old fat ugly delta over this, and you're going to solve a simpler problem. And you're like, okay, well, the problem's going to be pi over 4 plus pi k. And you're going to get the 1 in the first, and you're going to get the 1 in the third, is where it's going to actually happen. You can catch them both at the same time. And this is going to be equal to x over 2. That's what's going to be on there. Now, the reason why this generates less angles is because I'm not going to solve this the same way. Up above, I solved it with a fraction that I multiplied by, and it made the bottom get to be a bigger fraction, so ultimately more possibilities. This one we're going to multiply by 2 to get rid of the 2, and we're both basically going to multiply this entire conjunction over here, not square it. Oh God, gee, that's the wrong thing. We're going to multiply it by 2. Ooh, that's better. Okay, now if I multiply this guy by 2, my all answer will basically turn out to be 2 times this and 2 times this, and we'll end up with 2 pi over 4, 2 pi over 4, plus 2 pi k. Not 2 pi, yeah, plus 2 pi k, that's right. And this will end up being really pi over 2 plus 2 pi k. Now, if I go to start writing my answers, I'll be like, okay, the first one I'm going to write in the interval is going to be pi over 2. But then this tells me to add on to it 2 pi k, but that's going to make me go past the interval right out of the gate. And you're going to go past the 0 to 2 pi interval that we want to look at. It only has one answer. That's all it does, because the other answer is too far gone. The other answer would have been 2 pi added onto that, would have been like all the way around, it'd be like 5 pi over 2. That makes no sense. That's too far. That's beyond our 2 pi concept. We can't do that. So it only ends up with one answer instead of having multiple of them. Now, it could turn out, like I said, that you might run out of the interval before you even get to the actual wave itself. And that could be a possibility. Now, let's see if that happens on any of these other ones. I don't know. Maybe it could. Delta. When is sine 1? Sine's 1 at pi over 2 plus 2 pi k, and it happens only there. It's only 1 at that one spot, but it's going to be a multiple here when it's actually 2/3 x. Okay, now this one is kind of like the one before, but it's really not, because you have to multiply each side by its reciprocal 3/2 on both sides. 3/2. Now that'll cross cancel over there. We'll get x is equal to, well, let's see what happens when I distribute this bad boy. 3/2 is going to be 3 pi over 4, 3 pi over 4, plus 2 pi k times that is going to be 6 pi over 2, 6 pi over 2, which is 3 pi k. I'm sorry to say, but if I start running that on the interval, I'd be like, okay, 3 pi over 4, that works. But if I add 3 pi k, I'm going to go way past it. So the answer is only 3 pi over 4. Okay? So a basic answer of 3 pi over 4, that's all you got. Okay? Now, the last one that's listed here happens to be a cotangent. We don't get a lot of practice on this. Again, you're going to think of it as a delta that goes inside there. And you can be like, okay, when does cotangent equal root 3? Well, tangent would equal root 3 at pi over 3. So this answer must be at pi over 6. So the answer is going to be pi over 6 plus pi k is where it's going to actually happen. And if I run the answer as 2x right there, we're back to that old kind, the multi-angle that we did before. So we're going to multiply everything through by a half all the way through you. Let's see what we end up coming up with. X is equal to, I don't like that blue. It's just so weak. X is equal to pi over 12. Ooh, I like that. Plus, I'm going to run a half times that, pi over 2k. I don't like it written that way. I'd probably want it in 12ths. So its equivalence would be pi over 12 plus 6 pi over 12k. I'm going to write it this way so that it's easier to add things together. And let's see what we come up with as an answer. Must be pi over 12. There's one of them. Then I add 6 more onto it. Ooh, 7 pi over 12. And then I add 6 more. I'm back up to 13 pi over 12. And then I add 6 more, and I end up with 19 pi over 12. And we're going to get 4 individual answers. Now, I didn't see one that was in the notes that didn't generate an answer at all, that ended up with a no solution. Keep a close eye when you guys do your homework tonight, that there might be ones that are, that the angle is so fractional, like not a half angle, but like a fourth angle. A fourth angle will probably generate a no solution. That's probably the first time you'll run into it. Just be aware of that it actually can happen. Mr. Naughton is going to do the day 5 material for you guys in a little quick review and see how well you guys do for all the different kinds that you're going to see on the actual quiz and test. But you guys got this way under control. Just remember, solve a simpler problem and then resubstitute in so that you can get the multi-angles. Good job today. I'm super proud of you. You guys are doing great. And watch out for Multi-Angle Island. It could be a scary place.